Hi everybody, welcome to my last video on action potentials, action potential I guess, and resting membrane potential. I'm going to wrap it up here today and talk about the conduction of action potentials. Because we looked last time, if you recall, a single action potential, where you kind of rise to the threshold, depolarize and overshoot, and then hyperpolarize and undershoot, and come back to a resting membrane potential. So in this video, I'm going to show you how the action potential is conducted down an entire axon. I'll kind of do it like that or whatever. Here's our axon. So to get kind of a general sense for it, if you want to think about it as like burning a fuse. So when you burn a fuse, you light a match or a lighter or whatever, and stick it to the end of the fuse. I'm sure many of you have lit in like firecrackers or whatever. And as the fire sits on that fuse for half a second, whatever, it raises the temperature or whatever to a point where the end of the fuse catches on fire, and then it begins traveling, the sparks or the fire or whatever begins traveling in one direction. And the same thing is with an action potential. You have sort of a thing like some sort of fire or whatever to bring the membrane to threshold, and then that only goes in one direction. All right. But how it does this is just a little bit, just needs to be clarified. So pretend we have our action potential starting, here at the end of the axon. So action potential starting here. So what happens again? Well, you have an influx of, let's see, what did we do last time? Sodium, red. So you have an influx of wow, just struggling. All right. So, excuse me. Influx of sodium into the cell, big influx. And as you can imagine, this positive charge, while eventually, the sodium potassium pump, which we didn't really talk about, eventually gets the sodium back out of the cell. But when you have this huge influx of a positive charge, these ions start diffusing down the membrane. I'll make this even smaller, I guess, to prove our point. So sodium ions travel in both directions. And as they do so, this part of the membrane then depolarizes as well. Depolarizes enough to threshold, whereby these sodium channels in this part of the membrane then allow sodium to come into the cell again. Now, you're saying, well, hey, you just said that the action potential only runs in one way, but it looks like, sodium's diffusing in both directions. Well, while it's true that sodium diffuses in both directions, don't forget we have a refractory period initially, because, I guess this, for the sake of, the whole tie-in, here was our dendrite or whatever. And so, really, this part of the membrane is what's specialized. The axon is especially what's specialized to have these voltage-gated sodium channels, which are very responsive to these changes in membrane potential. And so as it goes down, you have that refractory period, both absolute and relative, that's stopping action potential from going in the other direction. So it continues to, the action potential continues to be conducted down the membrane. So that's the first thing is, so like I said, this keeps going. You end up getting more sodium. Gosh, it's frustrating. Here we go. You get more and more sodium every time just coming into the cell, only as the membrane depolarizes this way, right? because you open up the voltage-gated sodium channels. Now, as far as action potential velocity goes, the size of the axon actually matters. How big the diameter is allows for the velocity to increase or decrease. So as the diameter increases, so we have this type of axon, and then versus like this type of axon or something. You know, a lot of like the initial experiments on how we found out about action potentials was from a squid giant axon, and it was like 1 millimeter in diameter, something like that. And so it's just huge. And so these, and so in this case, in big diameters, it allows for the action potential to travel faster. Now, why that is because, so if you think about it, sodium can either go down this line, like in the membrane, within the axon, or, and this way, of course, or it could travel back out of the cell, by whatever mechanisms it can, like even simple diffusion or whatever. So because the smaller diameter, you have positive charges running into each other a lot more. That forces the sodium to want to travel out of the membrane more. Whereas in here, if you have just a bunch of, like little plus charges, then they're able to spread out more, and therefore they're okay traveling more down the axon, rather than being forced out of the axon. So that is not right, exactly. And so with the squid giant axon, the impulses travel, the action potentials travel really fast. One other way that thanks to evolution or whatever, that we can have an increase in velocity is by myelinating, by putting something called myelin sheaths around a membrane. So maybe we'll scroll down just a little bit. So if we have, kind of a thinner axon, you can put these things, I'm going to put them as, like orangey, and you can put these like capsules of myelin around the axon, and this basically, like, if you want to think of action potential conductance as being kind of like water traveling down a whole hose. If the hose is porous and you put tape around the outside of the hose, you're going to basically trap these ions inside and make them flow faster. That's exactly the same principle here. If by nature we had to only rely on super fast conductances being limited to giant axons, the source that I was reading on one of the books, it's actually called Neuroscience Exploring the Brain, 4th edition, by, I guess I might as well say, by Mark F. Baer. Anyways, they say that if our brain was like this big or whatever, like a squid giant axon, if our brain was composed of that many, our head would be so big you couldn't fit out like a barn door. So obviously that's not the case. So we use myelin instead. Myelin sheaths is what these are called. And you have these little, they call them nodes of Ranvier at each of these points where the myelin doesn't completely overlap. Yeah, but like I said, it basically just traps the ions inside and makes so that they can't get out. So it increases the conductance of the ions. So that's pretty much it in talking about action potential conductance. I hope there are more videos to come, and If there are, then please subscribe, because I mean that'd be a cool thing. So anyways, thank you for watching.